Okay, thank you very, very much. And it's great to be here, great to have been a participant in this meeting. I have to say that I've found many new things to think about that link to the things I already know about. That's always a stimulating and refreshing thing. I want to tell you a story that some of you will have heard parts of. Hopefully there'll be enough variations on the theme that it won't be identical to what you've heard before. And I want you really just to take you through some of the links that have been emerging between rough path theory, which started off tackling questions in stochastic analysis, stochastic differential equations of a quite technical nature, but a quantitative nature, and has actually substantially changed its targets. I mean, in one direction, it's gone off in Martin Heira's direction of stochastic partial differential equations, but in the direction I want to talk about today, it's much more to do with perhaps offering a mathematical insight into how one might do machine learning with stream data. And I want to emphasize one thing at the very beginning, and that is that I do not think it's a panacea. I do not think it's a recipe you can just plug in that makes things happen wonderfully, but it does give you understanding, and leveraging that understanding seems in a lot of situations to allow you to do things a little bit better than you were able to do before. I'm very grateful to have funding for doing this, and the funding is quite substantial actually, and we bundle it into two different projects really. An older project which we call DataSig, which is absolutely explicitly on this linkage that I talked about, and a slightly broader contract which we have more recently, which is actually about linking the mathematicians in our department with engineers in Hong Kong to try and do things of mutual interest and excitement. We do fundamental science, they're very focused on engineering, but there's a very conscious effort on both sides to build bridges that allow a flow of information between the two communities, and both of which are quite substantial and significant in funding the research I'm talking about. If you go back to my talk and paper at the International Congress in 2014, we were already very conscious of the fact that you could apply this understanding to the analysis of stream data. And I can't do much better than the words I chose then, I think. Rough path theory, well, that is a methodology for understanding the calculus that you use to describe the interaction between highly oscillating paths or driving signals and their responses when you push them into relatively smooth nonlinear systems. And the mathematics of that, as most people in this audience know, goes back a long, long way, and there are many different veins in it. Rough path theory itself, I think, picks out two particular veins as being very important. The geometry of K.T. Chen. K.T. Chen was interested in paths because he was interested in constructing the cohomology on loop space. And one of the things you want to do to understand the cohomology of something is you want to understand the functions on that space. And so actually, a lot of the technology, the iterated integrals, were studied by Chen because he wanted to understand in a canonical way the space of functions on streams. And the space of functions on streams is not so far today from what one might be interested in data science. On the other hand, everything I do has a quantitative and analysis basis, but when we mean things are close, it means we can prove they're close at some sense, and so on. And that analysis really came from Young. Young probably would have liked to prove the theorems we proved in rough path theory, but he didn't. And the reason he didn't, actually, I think fundamentally, is he didn't have Chen. It is the two together that actually makes the difference. Chen is what allows you to deal with things that are rougher than two. Two is on the borderline, Brownian motion's on the borderline. You can sort of use classical ideas and singular limits to get there, but beyond two, that's just not true. And since that time of the International Congress, things have moved on an awful lot. One thing that's happened is deep learning has happened. I mean, deep learning was an interesting new innovation at that time. And one of the things that was going on was my colleague and friend Ben Graham, who was at Warwick at the time, was developing some of the state-of-the-art methodologies for doing sparse convolutional neural nets. And he was interested in a competition for recognizing Chinese handwriting. So this is the online problem. You have a finger moving over the screen of your mobile phone. It produces a path in 2 dimensions, maybe 3 if you count pressure, but let's not worry about that. And you produce a path evolving in time, and you would like to do a classification problem of turning that path into one of 8,000 different characters, and you'd like to do it better than anybody else. And there's a reasonable data set of 2 or 3 million characters which you can use. Now, Ben entered that competition, and using his fancy convolutional neural nets and using a key tool that we had just established in rough path theory called the signature, he was able to win that competition. He won it quite decisively, despite very strong competition from the neural net people and things. We could spend a little bit of time explaining what he did to make it win. Essentially, he used a signature to do an early form of natural language processing. We will see later that the signature is a sort of way of a feature set that captures a path in an efficient way. And what Ben did is he colored his path with a color that represented these features. So at each point along the path, he gave a context. He told you through this vector of color what was going on in a neighborhood on the path. So he had a sliding window of signatures pushed back as colors along the path, effectively giving a context at each point along the path, which is what natural language processing is used for, right? To give a context to a stream so that the word he is replaced by all the information in he, so that you can see from the sentence it was Paul who was he, and that's what NLP does. It's what Google Maps does as well. Google Maps does not tell you anything you didn't know already. You can go and walk to find the location. It's extremely useful to have that information when you're standing here, rather than having to go and walk out to find it. This idea of contextualizing information, making it more Markov essentially, capturing the state you need to know how to evolve, is a powerful idea. And that's actually what they did with the Chinese handwriting, and they got a winning combination. That winning combination then went on to Guangzhou, who were a university department very interested in doing that kind of thing, and it went into an app, and a couple of million people used the app, and it got lots of great ratings. And then eventually that app was taken over by a big company, and one might work out that it's maybe used by 90 million people every day or something these days. So, but it gets more murky from that point of view because of NDAs and all that sort of thing. So that was the first application. That's what got me really interested in trying to be a bit professional about this. We got the people from Guangzhou over to Oxford. We actually started being quite serious about trying to understand. And so that's the beginning. Since then, there have been different success stories. I want to tell you success stories for the same reason I want to tell you it's not a panacea. The insights can be used to achieve, but you have to work at it. I can't do all the work for everybody. I'm not offering you a simple recipe. I'm trying to entice you that if you get stuck into it, you might get some feedback. So the second thing that was really successful was actually my student who now works for XTX, but James Morrill. And James, at that time a new student, was working. We decided to enter this competition. Well, we got enticed into it by one of my other ex-colleagues for the detection of sepsis. So here, the stream of data is all the information that's collected electronically about a patient in an intensive care unit. And this, by the way, makes a difference between where I come from and where much of these talks have come from. Very, very few of the time series I think about are nice and regular and things. They're not periodic, and they're not necessarily ergodic. They're complicated streams. But for sure, what happens is that they're typically multimodal, and what happens in the different coordinates, the order of that matters. But you don't have like infinitely long periods where you can try and recognize a pattern because it went like that or something like that. So this is a real difference. I am fundamentally focused on trying to do inference on data streams that typically have no natural periodicity. We may have lots of data, lots of different patients in the hospital, but we don't have periodicity or anything like that. Anyway, James was rather upset, really. We were all working on it, and he was chugging along at about halfway up the leaderboard in this competition. About 104 teams were in it, I think. It's sponsored by Google and run out of MIT. And he was about halfway, and then we realized that actually there was a bug in his code. And the bug in the code meant that we were using two incompatible versions of log signatures, whatever that means. And there was all garbage. The higher order things were just not being used. Of course, this was easy to fix, and the next time we put the Docker into the system, we leapt to the top place in the leaderboard. And we stayed there. And so that was a good illustration because it emphasized the fact that this extra information was doing something, but it also emphasizes the fact probably we would never have won had he not made that bug, because he worked so hard to get all the other things right. And it's actually the combination of getting everything else right and then doing this that will get you to the top. And more recently, in a very different direction, you can look at individual trajectories, but you can also look at ensembles of trajectories. And one of the things we'll talk about very briefly is expected signatures. Each of the trajectories has a signature. They're a vectorization of the data, so you can, if you have an empirical collection, you can take their expectation. Turns out it's a bit like a Laplace transform. The expected signature actually fully describes the empirical distribution. If you truncate it, you get a partial description, but a sophisticated partial description of the empirical distribution. This gives you a way of looking at a synthetic data set and asking in a relatively sophisticated way whether it matches the real empirical data set. It gives you a better way to train your GAN or whatever, so that you are able to generate high quality synthetic data. Constructing synthetic data is not trivial if you want it to capture the complex nonlinearities of the real data and you don't really know what they are. You want to learn from the data that it's like the data. It turns out that looking at the expected signatures and matching them is really a straightforward tool that is powerful in getting it much better than people usually do. It enabled Hans Buehler to generate loads of synthetic market data that he could use for his training of his deep hedging, which in fact got him recognition at the beginning of this year in Risk Magazine as Quant of the Year. So that's actually a very different, well, all three applications are very different actually. One was a classification, one was a sort of early warning, and this one's synthetic data. So it's all about describing involving systems. And here we see a strong parallel with many of the other talks. The goal of rough path theory, nothing to do with data science, the goal of rough path theory is to understand the impact of complex oscillatory systems. And you need to develop a top-down way of doing it. The whole failure of classical calculus, the whole reason it breaks down at some point is because it's based on the idea of looking at very small steps and working out what happens after each one, which works until you have more and more steps, the finer you go, to get more and more of the structure. So you need a better way of describing your stream data than simply giving values at times. And actually, that's what reservoir computing is. And that's what rough path theory is too. You don't describe a piece of data by saying, well, I'm going to buy a lot of analog digital converters and I'm going to sample the value at lots of discrete times. What you do is you look in your head or on paper or in reality at the impact of that stream of data on systems. That's what a reservoir computing is. It's looking at the impact of the system. Rough path theory differs from reservoir computing, not in that idea, but in the idea that it actually tries to identify a particular dynamical system, which is particularly informative, a generating function for nonlinearity, whereas reservoir computing chooses a random one with the view that typically the random one will contain all the information. There is no contradiction between those two, and from a mathematical perspective, they both need to be understood. But from a measuring point of view, the right way to understand a really complex bit of data is not to measure the values. It's to look at the systems you care about and see how they respond to that data. And this is actually a systematic way of dealing with things which is different to the sampling approach and far, far more effective, provably more effective. In fact, the lesson we really have is that most of data science, I think, prematurely digitizes. If you have a stream of data, the first thing you should do is let it interact with nonlinear systems, look at the outcome of those and digitize that. What you should not do is digitize the original data and then hope to replicate its effect on linearity, because you discover that actually the effects are caused by very high frequency oscillations potentially, and there's a far more data you need to collect to understand than if you did it the other way around. It's not a commutative process. And rough path theory is basically predicated on this view that you have top-down perspective on your data and you understand it through its impact on things, which is what we do in human life every day, right? A movie is quite a good example of a stream. How many of us describe a movie as a time series? The 73rd frame did this and the 85th frame did that. It's just not how we do it. We give impressions of intervals of the movie. Same with the book. We talk about the chapters, not the 53rd word. We don't actually do things in a discrete way. So we have a wonderful mathematical model for this sort of interaction. It's remarkably flexible and still mathematically precise. If we want to understand x over a time interval, we can look at the control differential equation and we can look at the response y at the end of the time interval. We can understand x better by changing f. That's not actually that different to what we do. Anyway, that is very much what we do. And what I want to get across as well is that once you relax to this level, once you give up the idea that it's meant to be some ergodic system or it's a semi-martingale, actually there's a huge amount of this stuff, you know? And moreover, if you have abstract ways of dealing with it, you can process it pretty much with the same software and the same tools across a very, very broad spectrum. You can set up your pipelines in the same way that you set up your pipelines for other things. The thing you have to remember, though, is that time series intrinsically are not a very efficient way of making that. Far better that your pipeline captured signatures over time or something like that. Or indeed your reservoir response over time. Yeah, basically summarizes what I've been saying for the last couple of minutes. I'm not going to read it out. So I want to explain a little bit the mathematics of this story. Somebody asked me a very good question yesterday. Yeah, you got this fancy signature, it's a feature set per pass. What makes it different to any other feature set? Why is it special? And I'm going to try and explain that. There are some clear mathematical reasons why it is quite different to most other feature sets. And crucially, it does exactly what things like wavelets do not do. If you have a multimodal time series, it's a big mistake to think of the modes separately. If you think of the modes separately, and then think, well, I describe each of them and then put them together, I have to be really, really careful in order to get the sequencing right. I have to resolve at quite high frequency, in some sense, each individual channel in order to get the interaction between the channels right. This turns out to be really quite an expensive thing to do in practice, and it's unnecessary, completely unnecessary. Your reservoir computing, your differential equation, can quite easily find that you went this way rather than that way. If you have nonlinearity in your control system, you have a second term. First term is the increment, which is the same for both of these, but the second term involves the area, and the area has a completely different sign. So in fact, you'll see the Lie brackets of these systems going in completely different directions according to which came first and which came second. And they're much, much coarser than looking at everything in very high frequencies and doing each coordinate separately. But in the talk, if I have time, I'm going to tell you a little bit about some recent things that have been happening as well as the basic maths. And I want to tell you about the idea of a neural controlled differential equation. I want to point out, and I think this is sort of an interesting case because it's really the data science going back to the math. We're going to find out that there is a good kernel for these paths, these streams. I can take two streams in the same space and I can take their inner product, so to speak. But the interesting thing is that you do it quite mathematically, and then you find out that it actually is solved by looking at a nonlinear hyperbolic, or a linear hyperbolic PDE, where the forcing is given by the paths and where the solution gives you the inner product. And you can do that with a GPU, and it's a classical 1920s PDE called the Gustat PDE. And I think that's interesting because that means you can do modern signature type analysis without ever mentioning signatures, because you can do it with kernels, and the kernels involve solving a PDE. So you don't ever need to use the word signature if you don't want to. You can just work with the PDEs. So as I said, this was the first stream data. And this is actually the original app, not the commercial app, but the original app. And it got really great reviews and, 4.8, 4.9 type scores and a couple of million people using it. And I used to have it to say things like Oxford and things, but anyway, it's a bit dated now because it got taken over by the big company and then they stopped maintaining it. But the stream data is really everywhere. But you can move, as I said, beyond stream data and think about ensembles of stream data and making predictions from them. Of course, they are also streams of data, but we'll see that there are actually tools that can be useful for understanding those. And I guess our team has three focuses, right? One is basically classification, understanding what you're seeing. Is it a child? Which letter is it? So on. There's always an interest in predicting what happens next. If you have observed somebody for 20 years and you've observed lots of other people for their whole lifetime, you'd like to know what the probability is or how their cognitive skills are going to evolve in the future. because you'd like to know whether they're likely to get dementia or not. I mean, there are always interest in taking corpus of data, corpus of complicated streams, and using that corpus of complicated streams, plus somebody up to half time, to give some understanding of what the future of that person is going to involve. These are very generic questions, actually, that do not need to revolve around Alzheimer or anything else, and they are fundamentally of interest to us. Anomalies is another one which is really incredibly valuable and incredibly generic. You have an ensemble of trajectories, and now you have another trajectory, and you'd like to have reasonable ways of deciding whether that new trajectory belongs in the class you already have. And again, you can do sensible things like that because we have canonical ways to vectorize this data. You could say time series are a canonical way to vectorize data, but I'll explain why that is actually a crap way of vectorizing your data. Okay, so now some mathematics. Now I'm going to try and explain to you one of the key mathematical ideas. And in a sense, it really is the answer to the question, why use signatures? If I have a time series and I want to learn whether A comes, let's suppose it's a three-dimensional time series. So we have signal in 3 dimensions. And I want to know whether the event in channel A happens before the event in channel B and happens before the event in channel C. That's actually a cubic relationship. You can detect it with cubic polynomials. There's a problem. The dimension of the space of cubic polynomials is astronomical. If I have sampled this 700 times, I actually have 700 cubes, cubic polynomials. So you're not going to learn this relationship with a few thousand data points. And this, I think, is a fundamental reason why people don't do these things. The fact is that capturing order of events is quite a complicated thing if you regard your original data as simply a vector of time series points. RNNs, LSTM, they can do these things much better. But the basic problem is that the space of polynomials on this data, if you vectorize it as a time series, is absolutely horrendous. And it's because there's a symmetry. And data science doesn't like symmetry. Data science hates symmetry, because what does symmetry mean? It means there are different ways of representing the same thing. So you have to learn from your data that they're all the same thing again. And whereas that symmetry might not matter very much if it's just a 7 and you rotate it on the table and it's a rotation group of symmetries, because that's just a one-dimensional group of symmetries. And you might well learn that. There's a hidden symmetry in time series data that people often forget about, and that's the sampling rate. You know, you have books about irregularly sampled data or missing data for this reason, because they don't see it as just a symmetry. It's the symmetry of reparameterization of your path. That 3 is obviously a 3. But if I were to write it as a time series, not so obvious. That's the x coordinate, I think. It could be the y. And what's the difference between the dotted and the solid line? Nothing, except that you ran the thing at a different speed. You drew the 3 slightly differently. But the time series look fundamentally different, as they will, because you move the stuff from one end to the other. And you can put the 2 side by side, and you still won't recognize very easily that it's a 3. And you see, the point is the representation is wrong. The representation as a time series is really not very helpful. We as human beings have absolutely no difficulty seeing there's a curve there. But if you view it as a time series, it's not so simple. And the problem is that I can reparameterize that path, and it's the same object. And the other problem is, that's your symmetry, because you can unreparameterize. It's a group. The problem is it's a very, very big group. Not a little group, it's not one-dimensional, two-dimensional. It's a horrendous infinite-dimensional gauge group. And so most of the time, when people write down time series and they're trying to learn these things, they're trying to learn that there's an infinite-dimensional group of symmetries there. You know, that they're all representing the same object. And you're sort of screwed, right? The point is that it's not true that your data is living on some manifold. There are fibers given by the symmetry, different representations of the same object, and that bit is absolutely huge. And this actually is the reason signatures work, or can work, I should say. It's because they quotient out that. Because when you look at a controlled differential equation, it respects this parameterization rather well. If I don't put time in separately, I can have time, but think of it as part of my state variable. Then if I speed up the input, if I sample it at a different rate, I simply speed up the output. So if I look at the response over the whole interval, it actually filters out this group of symmetries. Just like understanding the 7 without the rotation, but it filters out the rate at which you sampled the data. So it means that your time series gets a feature set that doesn't depend on how often you sampled it. And yeah, now you'll have to really, because of my hearing, somebody has to, if you can tell me what he says, this might work.
So the question is, when you say there's the reparameterization, this makes sense in discrete time where you have a sequence, k plus 1. But if you know real time, doesn't that collapse the symmetry? If I tell you the actual times that things happen and then you do things in continuous time, doesn't that flatten you onto one fiber?
No.
No.
I think not the way I'm thinking about it.
Okay.
I mean, that 3 is the same object regardless of how quickly I went around it. But they will give those, you didn't see the sampling on those curves. You had different representations and the same 3, right? Actually, people are going to say, but time matters a lot. And the answer is yes, time does matter a lot. But if the way, that's why I use the word sampling rate, because I think the way to deal with that normally is to add time as an extra state variable. So you think of x, y, t. And you can immediately see, because we will see that now the dimension of our space of polynomials of degree 3 is like the width cubed, and so on. So, and it's finite dimensional, and it's not affected by the sampling rate. And that's still true if you have time in there now, but now you get polynomials of time as well. So if the parameterization is important, then doing it this way allows you to become more and more flexible about time parameterization as you increase more variables into your feature set. But it doesn't all of it do it with a big bang, where you allow all parameterizations right from the beginning. I don't know if that's very clear, and we can have a discussion afterwards. But that's the point, right? The point is that what we're really interested in is how to describe, well, the signature offers a way of describing a curve that's good in lots of data science ways, but is also forgetful in a very precise sense of removing the parameterization. It captures the order in which things happen and only the order in which things happen. So the basic idea then is actually to use reservoir computing in some sense, right? It's to represent the data over a period of time by its effect on the system. That very conveniently ignores the speed at which you travel along it. If you think that's important, then include time as a parameter, not, so as a value, as a state variable, not as a time parameter. Don't think of it as a time parameter. Right, so that's the broad idea. And that collapses infinitely many dimensions out of your system. Unfortunately, it leaves infinitely many in, because there is no doubt whatever that trying to understand complex multimodal data potentially has lots of exponentials in it. Right? So this is why it's never a panacea. It removes a very expensive item, but the basic problem is already exponential. And so you shouldn't necessarily expect miracles. Okay, but what you can do is be clever about your reservoir. Instead of randomly choosing a system, you can actually choose a very careful system, which is actually just like the exponential function, except there's a non-commutative product in there. So if you think of your path gamma as living in a vector space, then this thing, well, if S was scalar, then the left-hand side will become a vector. If S was a vector, the right-hand side will become a 2-tensor, and so on. So you see that the solution to this actually is a sequence of tensors, one of each degree. So you've taken your stream of data and you've turned it into a stream of tensors. And those tensors give a description of what's going on. They are, the coefficients of those are, if you like, polynomials on path space. Actually, this is true in many ways. They're a generating function. In fact, any function, going back to the universality discussions, any function on the stream that is on unparameterized paths can be approximated by these polynomials. And these polynomials are functions on the unparameterized path. So it's a very reasonable transformation. And you can rewrite it, but this goes back to our earlier discussion, actually. In some ways, this is not what you want to do. It's what's forced on you by people prematurely digitizing things. But you can write these polynomials as integrals iterated many times over your path. Notice it's the exact opposite of Fock space in that you have an ordering here. You integrate over a simplex. One of the consequences of that, by the way, is that there are n factorial simplexes in a cube. So these things behave roughly like a factorial. And although they're exploding exponentially in terms of their number, they're dying factorially, and the factorial wins. So you get an analysis, a good analysis, and you get finitely many of these things telling you what's happening in any given case. That finite number can be very big. It's a theorem, genuine theorem, quite a hard paper really, actually, if you look at it. I look back at it with some amazement that we managed to write it. That actually proves that this sequence of integrals completely describes the path up to reparameterization. And the notion of reparameterization is made very, very precise. There's a notion of tree-like equivalence or null set. And in that way, it's a bit like Fourier series. You know, a Fourier series does not characterize a path. It characterizes a path up to the correct notion of null set. And that's exactly the sort of thing that happens here. But the right way to think about that, people say, well, if it has an increasing path, then it's unique. Sure, but that's because then you pin down the reparameterization. I think the right way to think about it is just to say there is an appropriate generalized notion of reparameterization, and the signature exactly characterizes the path up to that notion of parameterization. So it's a feature set that is faithful, except that it's factored out this infinite dimensional nonlinear group of symmetries. But it has some nice properties, and one of the properties is that it's sort of linear, it's a vectorization, and you can take the individual coefficients in front of the individual words that form the basis for the tensor products, and they are individual bits of description of this path about the order in which things happen, And you can build them as functions. You can think of them as the basic functions on path space. This is used in finance. It's used all over the place now. It actually drags you quite quickly into relatively deep mathematics of the algebraic kind. There are books written in the 70s about Freely algebras, Bourbaki, and so on. And you find they're really telling you things that are actually useful and meaningful in this story. One of the interesting questions that is pure maths is that it's pretty obvious that each of these features is an integration, and you can do it, and it can be expensive and physical, but there are also algebraic relationships between them, so you don't need to do them all. Which ones are pure computer algebra, and which ones actually involve tackling the signal is an interesting question, actually, which has got some serious open questions even now. So how do you organize your data? It's sort of a bit like a structure theorem for matrices. You know, you can always write a matrix as a product of diagonal and upper triangular and so on. There are similar theorems here that you can always get your information as computer organized polynomials in certain basic facts and things like that. So there's quite a lot of pure math that can really be done. There's something called the log signature, which is important, and will be very important if I wanted to explain the relationship between this and Koopman operators. Yeah, so I just want to focus really on these 2 points now. As I said, the signature is a vector. It's now a graded vector because it's tensors of degree k. We can throw away the high dimensional ones if we want to. So then we can take expected signatures, and they're a good proxy for describing empirical measures. This is a powerful thing, right? You know, that's what the martingale problem was all about for semi-martingales, was how you describe probability measures on paths. This is a straightforward way of describing a measure on multimodal paths, empirical multimodal paths, that is actually pretty sophisticated in terms of comparisons. And there's a natural kernel, so you don't even need to get involved with signatures if you don't want to, and you're happy working with kernels. And here's this PDE. So at one level, the PDEs, the kernel is trivial, and then there's a kernel trick, which means it's usable. So the kernel is simply, you've got this signature. The signature is indexed by words. Every word is a basis element for one of these tensors. And so you actually have a series of coefficients in front of every word where the letters generate your vector space. But you have 2 paths, then each of them generates all these coefficients. If you think of the letters as being orthogonal, then you can obviously take the pairwise inner products of these 2 signatures. And we can call that the signature kernel. It makes sense whenever there's an inner product structure on the original vector spaces. And it converges. It converges because, as I said, you have exponentially many terms, but they decay factorially. So actually, you can prove that this sum is always finite. And it's finite for rough paths. It's not just finite for bounded variation paths. The amazing thing is that Harold and Franz realized that actually by messing about in originally, and now in a more principled way, there was actually a kernel trick. So you could actually work out the kernel between 2 of these paths without computing the infinite series and pairing them all off. And that was really a good remark. And then Chris Salvi at Imperial, and myself and others, working on it, sort of triggered by Franz and Harold's work, identified a PDE that you could solve to actually get this inner product. And here, this is the PDE. So K, if you like, is the inner product between the path defined on this time segment and the path defined on this time segment. And let's assume the paths have finite length, so they have derivatives. Then this is a PDE, a second order hyperbolic PDE that you can solve. And you can solve it. You can do it with a GPU, you can do it quite efficiently. So this offers quite an exciting thing to be able to do too. Signatures can be inverted. You don't know the parameterization, but this is work by Weixin Yang, where he actually has developed some quite nice software based on optimization that looks for the path with given signature. And you can see that, you know, these are not very deep signatures actually. Basically, the depth of the signature is going to correspond to the number of turning directions that you have. You wouldn't be able to do this with less than about 4 or 5 terms in a signature, but you can definitely do it. And you see, therefore, that those coefficients summarize these quite complicated curves. And this is modern data for you, right? So modern data is just streams of paths. In fact, this is shipping data. And this is actually malware data. So here there are trees. These are ensembles of paths. And what they actually are is that when you log on to a computer, you create a process, and that process creates sub-processes that create sub-processes. And as they evolve, they have properties like they write files or they get some more memory. And just by keeping the log of those basic events, you can create a tree of processes associated with any given logon. And there we're trying to use that information in malware context to try and recognize when you have a path that is an outlier, or in this case an ensemble that's an outlier, so that you can detect that something is not quite right. Yeah, so this is the... So we're very interested in outliers, and they have lots of applications. We have another project where we're looking at where the outliers are used to pick out the intervals of time when radio telescope data have interference. But again, the point I would try and get is that stream data for us is a generic type. Stream multimodal data, and we develop the tools and the software. It is surprising how flexibly we can move them around. We can make the tools work better with examples and real data and real challenges. But the goal is to create universal tools. This is a universal tool that I'm talking about now, which is very related in a sense to the lecture you gave yesterday morning. So the idea is that you have an input stream and an output stream. And what you would like to do is learn the functional relationship between the two. Now, one way to do that is like an LSTM or something, and you learn the LSTM. But the other way to do it, just as Ricky Chen's stuff on differential equations was effective for functions, you can imagine that you have a physics that does this, a differential equation that links the two together, and you can try and learn the physics. So effectively, if it were a differential equation, you'd have your neural net trying to find a vector field. If it's a controlled differential equation, you try and find basically a family of vector fields. And then the input controls the output, right? And that has its problems and all the rest of it, but it can be done. And also, it can leverage much better understanding of the differential equation literature, the control rough path literature, because we know how to solve these equations globally. We don't have to go down to the microstructure like the LSTM. We know how to approximate the change in the y given the change in the x macroscopically. That's what rough path theory is about. And we use something called the log signature and the map from the free Lie algebra into the Lie algebra vector fields. Basically, that whole process takes a piece of path and translates it into a time invariant ODE, vector field, which you solve over the unit of time to get to the next place. Now, this is an expensive thing to do, but going right back to papers in Siam, I can't remember, 1995, it's an efficient thing to do if the differential equation is quite expensive to compute. And the reason it's expensive is you need to compute all these areas and things. Right? What really changes here is that when you're training a neural net, you ultimately need to solve millions or billions of differential equations, all with the same driving noise. So this completely amortizes the cost of doing this complicated calculation of the signature, because you only need to do that once. That's really being applied to the inputs. It's better describing the inputs, and then you get that benefit every single cycle of every single training step after that, which is really a big plus. And it also has the advantage of meaning that you have far fewer problems of collapsing gradients and things, because actually you have far fewer steps. You don't have millions of steps just because your original data have millions of steps. You have maybe as many steps as you can cope with given your gradient collapsing, and you do your best. But it allows you really to get around both those things. I don't know how we're doing for time, but we're probably running out. Yeah. So if you were reading this, I would start with the most recent paper and sort of move backwards time-wise. Our team seems to be doing quite well at the moment, and I was absolutely over the moon that we managed to get 4 papers into NeurIPS this year. Not all of them on this sort of topic, though. So I just want to spend a couple of minutes talking about ensembles of paths. So ensembles of paths, I've mentioned before, is a genuine and important data set type. This is where you don't have one path and you're trying to make, you have a distribution on paths and you're trying to understand the distribution. And you're trying to make inference based on the distribution. And one of the examples we did to show you could do this with expected signatures was actually to do with agricultural crops in France based on aerial satellites. And there, the individual trajectories were the behavior of the individual fields. And each of those was like a controlled differential equation, but you could use kernel methods, and you could aggregate them, and then you had the bigger things, and you could understand the impact of policy. And anyway, when you put this all together, you win, and you do better than everybody else. But it's, again, showing the flexibility, I think, of the expected signature, the signature, giving you this standardized way of thinking. Not a panacea, though, right? You would never want to use the whole signature over a long period of time. If you have a long period of time, you're almost invariably going to take the signature over short bits of time, but you're not going to go down to the piecewise linear. The optimum is somewhere in the middle. It's not at either extreme. Yeah. I'll just finish with this, not because I'm going to talk about it, but just because it has some fun pictures. So this was one of the things we did quite early on and demonstrated we could get state of the art at the time. We've not really followed it up. I don't think we're getting state of the art now, but we just did it and were able to. And that was really how you make sense of motion of people based purely on knowledge of the landmarks, which de-identifies people to a substantial extent and allows you to do lots of things that you wouldn't be able to do if you actually take photographs of people. And it's surprising how much information is contained in those landmarks. I mean, it's not hard to guess what this person is doing, you know, it's just not hard, right? But equally well, they're paths now, aren't they? They're paths in something like a 26-dimensional space. And so now we're in this space where we have more of a canonical way of looking at things. We have methods now which we didn't have then for dealing with dimensionality, but they're open still. Anyway, I'm just going to finish with that one. to show you probably can't tell what's going on. So what do you think you're seeing there? When I click, you'll realize that the characteristic feature is not one you thought about. Right. So thank you very much for listening to me for this time. I hope I haven't overrun. No, I think I've got a couple of minutes left. I'm happy to answer some questions. And thank you very, very much for organizing the meeting. And thank you all for coming to this first talk on the last day, which is probably a pretty grim time to be here. Thank you all. Bye.